Hi, in this video, I'm going to talk about how a laser works. I'll go through some PowerPoint slides describing the basic theory behind a laser, and then we'll look at some examples. All right, so hang on and we'll get started. 1 second. All right, so a laser, of course, refers to light amplification by stimulated emission of radiation. So we have to talk about what those things mean. So first, light amplification. Inside of a laser is a medium that's designed to amplify light at a certain wavelength or band of wavelengths. So this amplifying medium is shown here in our cartoon picture. The amplifying medium has to be supplied with energy, so it's pumped by some external energy source. But in its operation, light that passes through the medium will be amplified. It will be brighter when it emerges than it was when it entered. Then this amplifying medium is surrounded by a cavity, that is a set of mirrors that reflect the light back and forth through the amplifying medium. So we have an amplifier and we have positive feedback from the mirrors. And this creates an oscillator, something that has gain and positive feedback and will spontaneously start to emit power, in this case light, once it's turned on. In particular, one of the reflectors is made a high reflector or total reflector that reflects nearly all of the light that strikes it. The other one is a partial reflector so that some of the light can leak out to be an output beam. So the next thing we want to talk about is how this amplifying medium works, okay? It works by stimulated emission of radiation. Well, what's that? So we have to look at the basic physics of an atom interacting with light. So let's think of an atom, and let's imagine we can ignore all of the energy levels except the lowest one, the ground state, and the next one. So we just have two states. There are three different processes that can take place. If the atom starts in the ground state, then it could absorb a photon of the right wavelength that would kick it up into the excited state. This is called absorption. Or here in this drawing, it's called stimulated absorption because the transition takes place in response to being stimulated by a photon. Okay? The second process is spontaneous emission. This is a familiar process where the atom starts in an excited state and then it spontaneously relaxes back down to the ground state and emits a photon. Okay? Spontaneous emission. And spontaneous emission is actually a little bit weird because it's saying here's something that happens, but it just happens spontaneously. There's no reason why it happens. It just happens at random. Anyway, spontaneous emission. The third process is called stimulate emission. Here, an atom in its excited state is disturbed by a photon, which excites it in just the right way to drive it from the excited state back down to the ground state. And when it does so, it emits another photon. And the second photon is essentially identical to the first photon. That's the same wavelength, and it's in the same radiation mode. It's moving in the same direction, and so on. To us, stimulated emission seems weird because we don't see that every day. But in some sense, it's easier to describe than spontaneous emission because here the atom is responding to an excitation. It started in a long-lived excited state, and then when it was disturbed in just the right way, it made a transition to the lower state. Actually, stimulated emission is a lot like absorption. Only in absorption, the photon kicks the atom up. In stimulated emission, it kicks it down. But they're essentially the same process. Here's another way to look at these. We have our lower level and our upper level. We can make transitions between them through absorption, where the atom is excited from the lower state to the upper state by absorbing a photon. There's spontaneous emission, where the atom drops back down to the lower state and emits a photon. And there's stimulated emission, where a photon passing by disturbs the system and drives this transition from the upper state to the lower state, creating another photon. Okay? And in some sense, stimulated emission is absorption run backwards. Now, to describe these, well, one second. Okay, we can describe the rates of these different processes. Let's let W12 be the rate of transitions from the lower state to the upper state. Then this rate must depend on at least these following things. It must depend on the number of atoms in the lower state. If there aren't any atoms in the lower state, then there's no way we can have a transition out of that state. So W12 is proportional to N1. It's also proportional to the intensity of the light, or the energy density at the required frequency, U sub nu. And finally, the rate is proportional to some constant that contains all the rest of the physics that we're not interested in right now. Likewise, we can describe the rate of transitions from the upper state back down to the lower state. Here we have two terms, one describing spontaneous emission and one describing stimulated emission. Okay? The spontaneous emission term, AN2, is proportional to the number of atoms in the upper state. Again, no atoms in the upper state. You can't have transitions out of that state. But it doesn't depend on the intensity of the light because it's spontaneous. The second process, stimulated emission, also depends on the number of atoms in the upper state, but it has to depend on the light intensity as well, because we need photons in order to drive this process. Finally, it depends on a constant here, which again contains all of the rest of the physics that we're not interested in talking about. And something that's interesting, it turns out that these two constants, the B here and the B here in the stimulated emission, these are the same, something which we can prove, but I'm not going to do that right this moment. Okay? Now, armed with that knowledge, let's take a look at some processes. First, let's suppose we have a number of two-state systems. These are a number of different atoms. Each atom can either be in the lower state or in the upper state. Let's suppose that the light intensity is high, so that the rate of absorption and the rate of stimulated emission are each much larger than the rate of spontaneous emission, so that for the moment we can ignore spontaneous emission. Finally, let's imagine that there are more atoms in the lower state than there are in the upper state. This is the normal situation, but let's imagine that that's so. Then when light interacts with our system, we're more likely to absorb a photon than we are to drive stimulated emission, simply because there are more atoms in the lower state than there are in the upper state. As a result, when light passes through our system, it will predominantly be absorbed. And so the light that comes out will be weaker than the light that went in, because the light has been absorbed to drive absorption from level 1 to level 2. Suppose, though, we could arrange so that the population in the upper state was greater than the population in the lower state. This is very unusual. A system like this is called an inverted system. And we don't come across these every day. But in an inverted system, the physics is just reversed. Now, when light interacts with this system, it's more likely to drive stimulated emission than it is to drive absorption. So light that travels through such a system is predominantly amplified because stimulated emission dominates over absorption. And look, the only thing that was required to get amplification instead of loss was to have our system be inverted, to have more atoms in the upper state than in the lower state. Okay, well, now I'd like to talk briefly about how we could arrange to have more atoms in the upper state than in the lower state. Well, to do this, normally we can't use a two-level system. We have to use something more complicated. So one type of atom might give us a four-level system, where we can excite atoms from the lowest state to an upper state by absorbing light or some other way. But in some way, we can populate this upper state. It's very difficult to get a population inversion between state 0 and state 3 here, but we don't need to do that. Instead, once the atoms enter state 3, we pick a system where they will rapidly decay to some intermediate state, state 2. And we'll make the normal lifetime in state 2, kind of long. In that case, the atoms will get pumped up and they'll accumulate in state 2. When they make a transition down, they'll end up in state 1. And then we arrange a system where state 1 decays very rapidly to the ground state. In that case, it should be easy to arrange a population inversion. If we pump rapidly enough, atoms will build up in this long-lived state 2. Meanwhile, state 1 has a low population because it decays so rapidly. And so we can get a population inversion between state 2 and state 1. Then we're all set. If we excite the system with photons whose wavelength exactly matches the 2-to-1 transition, we can get light amplification and lasing. Here's a very bad cartoon picture of what might happen then. So we set this up, we start pumping our amplified medium, and then the following happens. So initially, the light intensity in the laser is low. So the only process that happens is spontaneous emission, or fluorescence. So spontaneous emission occurs, photons are going off in all the random directions, but occasionally one goes in the direction such that it will hit this mirror and go back through the amplifying medium. When it does that, it will drive stimulated emission transitions and come out brighter, more photons than went in. If these are directed properly, they'll bounce off the other mirror and be sent back through again, and be amplified further. And this light will bounce back and forth until all the energy that's entering the system through the pump is being used to create photons and stimulated emission. And then we'll have a high light intensity in the laser, and we'll have a steady stream of photons coming out of the partial mirror. Okay, and that, at the most basic level, is how a laser works. I'm going to stop here, and then we'll pick up the story in the next video.